about Cherenkov Telescope Array and the TeV sky. Since the focus of this conference is optical near infrared, at first I'd like to tell you what CTA is. Then I tell you about the gamma ray sky. Then I tell you about CTA science cases. And then I get to the main point, which are CTA surveys. Now, if you want to remember one thing from this talk, is the following. There are no flux-limited complete surveys of the TeV sky at present. So anything CTA will do in this regime will be amazing. I repeat, no flux-limited complete surveys, so it's going to be fantastic, whatever it finds. So to put things into perspective, CTA is going to be the largest ground-based gamma ray observatory in the world, 60 telescopes. It is going to be, of course, better than what we have now. Now we have HESS, MAGIC, and VERITAS by a factor of between 5 and 10. And we have two sites. One is close to Cerro Paranal, and the other one is going to be La Palma. And according to the project scientist, Roberto Zanin, science operations should start by the end of 2025 at the earliest. Anything you want to know more, it's on the CTA website. A disclaimer, I'm not part of CTA. I'm just an ESO astronomer working also on high energy astrophysics, so I was asked by the organizers to give you an idea of what's in store in terms of CTA surveys. So this is Paranal there, Armazones, where DLT is going to be. This is the location of CTA South. This is a picture I took when I went with Michele a few years ago. We are driving from Armazones back to Paranal, and that's roughly where CTA South is going to be. This is a picture from the CTA website. So it's a plateau, which is perfect for them. Logistics is going to be provided by ESO. Just to put things into context, this is the spectrum. I put some facilities there. La Silla Paranal Observatory, optical near infrared. And then I put SKA radio, ALMA Apex millimeter, ELT, of course, X-ray. So CTA is going to be sampling the 20 GeV with the 300 TeV sky. GeV is a billion, TeV is a trillion. Fun fact, the kinetic energy of a flying mosquito is 1 TeV. So it's imagine a photon which actually has the energy of a mosquito, which is actually quite impressive, I think. And also another impressive thing, CTA will reach energies above those of the LHC, the Large Hadron Collider at CERN, and so it's actually going beyond what we can do on Earth in terms of accelerating particles. Now, as you all know, any radiation about the UV band is blocked by the atmosphere, so how can CTA actually study the gamma ray photons? Well, what happens is that, making a very complicated story short, you have a gamma ray photon impinging on the upper atmosphere. It produces particles, which produces photons, which produces particles, so a cascade, and the high energy photon is degraded to optical photons, which are seen by the CTA telescopes on the ground. Now, Cherenkov, he was a Russian physicist who got the Nobel Prize because he was the one detecting Cherenkov radiation, which is what you get when you have particles moving faster than light in a medium. So you get the characteristic blue radiation, which you also see in nuclear reactors, and this is why Cherenkov detectors use the same principle. And again, so to repeat, you have the high energy gamma ray photons is destroyed in the atmosphere, producing a cascade all the way down to the optical band, where we actually can see with CTA and other telescopes. So now I have to walk you through the high energy sky, which is very different from what you're used to. So I spent some time there. This is the high energy sky. Then I move to the very high energy sky. So for us, high energy astrophysicists, the high energy sky is between 50 megaelectron-volt and 1 TeV, and it's provided by Fermi, this catalog. Fermi is a space mission, is constantly surveying the sky and detecting sources. And right now, the latest catalog is about almost 7,000 sources. This is a projection on the galactic plane. You see a bunch of galactic sources here in red, and then you see many, many galactic sources. So I looked at the latest catalog and put a table together. So what you see that about 8% of the sources are galactic, pulsars, pulsar-wind nebula, supernova remnants. Then you have blazars, 33%, blazars of a certain type, 28%, other sources beyond the galaxy, just 1%, and you have unclassified sources. Most of them are going to be blazars. So there's something going on there. Blazars make up between 60 to 90% of the Fermi sky. So at this point, I have to tell you what blazars are, for those of you who don't work on blazars. I'll make it very short. We know that there are about 2 trillion galaxies in the universe. We know that most of them have a black hole at the center. In most cases, black holes are doing nothing. They're just sitting there, like in our own galaxy. In about 1% of the cases, there is matter falling onto the black hole, converting its gravitational energy into radiation. The nucleus becomes active. We call them AGN. In about less than 10% of the 1%, we have jets. Jets are streams of particles moving very, very fast, close to the speed of light, by some processes which start close to the black hole. When the jet is pointing towards us, we call the object a blazar. So if you do the math, a blazar, only one galaxy out of 100,000 is a blazar. So they're very, very rare, but they're extremely powerful, and especially in the gamma ray band. Okay, now I'm moving to the very high energy gamma ray sky. So there are about 272 sources detected above 1 TeV by Cherenkov Telescope so far. Again, HESS, Veritas, and MAGIC. This is a table. Notice the drop, okay? It's almost 7,000 by Fermi, now about less than 300. And so here now the source population is slightly different. So we have a third galactic sources, 30% blazars, other AGN, and then many are classified, which are in this case mostly galactic because they are on the galactic plane. So in this case, blazars make up about a third of the TeV sky, but 86% of the galactic sky. As you can see, there is a very, very strong component of galactic sources. Now, I will describe some of these sources because they might be obscure to you, like Passaway Nebula, in the next slides. So the first point to notice and to bring home is that the drop of about a factor of 25 from Fermi to the TeV sky. Why is that? 3 reasons. Number 1, sensitivity. Fermi is much more sensitive than HESS, Veritas, and MAGIC. Number 2, many sources are actually falling off at high energies. Guys, getting a TeV photon produced is very, very hard. So many sources, I'm showing you some blazars here. So in red, you see a BLR, which is a class of blazars. It's actually peaking, as you can see, at the TeV band, while flat spectrum quasars, another laser subclass, as you can see, they peak way before, and by the time you are the TeV band, you're dropping. But the third point is that your galaxies, the optical near-infrared galaxies, produce photons, and when a gamma ray photon is coming from another galaxy peacefully, it gets destroyed by photo-photon interaction, and therefore the 1 TeV horizon is very, very small. We don't get TeV photons above ratios of 0.03. And this is beautifully shown here. This is a plot from the IceCube collaboration. I'm showing distance in megaparsecs versus energy. So TeV is here. PeV, that's 10 to the 15 electron volt, is there. So what you can see that we don't get, so above 100 tera electron volts, you only get galactic photons, nothing else. Everything else is destroyed by gamma-gamma interaction due to the presence of optical near-infrared photons produced by all the galaxies in the universe. So because of these things, the very energy gamma ray sky is less populated at the moment than the Fermi sky below 1 TeV. Okay, now you are working on your surveys, optical near-infrared. You must ask yourself, why should I care? The classic question, right? And the answer is that, so first of all, why do we care about getting high energy gamma rays? Well, the answer is the following. That as I told you already, gamma ray photons are the most energetic ones in the spectrum, and the only way you produce them is by having some extreme phenomena and some extreme physics. So they give us a window on very rare and explosive events. And there is another very interesting part. You guys study thermal processes, black body. The particles and the photons are in equilibrium. If you had the black body peaking at GeV energies, the temperature should be about 4 trillion Kelvin. Nothing in the universe can be so hot. So the answer is that these photons are not thermal, they are non-thermal. And so they're not black body, they're not peaked, there are power laws covering very orders of magnitude. So again, very energy sky give us a window on non-thermal processes related to black holes, neutron stars, jets, and so forth. CTI science. So what are the science cases? So there was a book published about 6 years ago, and this is the 3 themes that actually they discussed there. I go quickly through all of them and then concentrate on a couple of them. Number 1, cosmic rays. I'll tell you in a minute what they are, but the question here, how can you accelerate cosmic rays to the energies that they have, which are amazing? I'll tell you in a minute. And what are the sites, what are the sources producing cosmic rays? Then, as I said earlier, extreme environments, so neutrons, black holes, winds, explosions. And the third one, which I won't touch, it's actually quite exotic and cool, dark matter, axions, and quantum gravity. And getting finally to the core of my talk, which is CTA surveys, now that you know everything about CTA and the gamma ray sky. The same book, the table of contents, describes the KSP, the key science projects, and many of them are actually surveys. And I'll concentrate on 2, galactic plane and extragalactic surveys, and giving you in the meantime some details about the typical sources which make up the skies. So, by the way, the book, as I said, is 6 years old, so I looked for more recent updates, and in this case, I found one. There is a paper which is 2 years old, which gives you an update on the galactic plane survey by CTA. So the main point, it's going to be a survey lasting about 1,600 hours over 10 years, and the main classes of gamma ray emitters in this case are pulsar wind nebula, supernova remnants, and gamma ray binaries. So what these authors did, they basically did a simulation. They put everything they knew about these galactic sources into a computer, and they simulated how many sources this survey is going to detect. And this is number counts. I guess most of you are familiar with it. You plot number of sources above a given flux, and this is a flux in these units, above 1 TeV. So as you can see, the known sources converge pretty quickly. It means basically this is the limit of what you can do right now. And the target of the galactic plane survey is here, about more than an order of magnitude fainter. And actually here, you see the number of sources in the case of the pulsar wind nebula as a function of flux. So the ones we know right now, it's the green, small down there, and CTA will detect about 7 times more sources. So again, an amazing improvement, and again, a flux-limited complete survey, which we don't have at the moment. So what are pulsar wind nebula? I had to struggle as well, because so you have supernova exploding, neutron star starts spinning, you have a pulsar. Then the pulsar has relativistic wind, and the wind creates a shock, and beyond the shock, downstream the shock, there is a pulsar wind nebula, which produces a bunch of photons, including very high energy. So whenever you have a pulsar, you also have a pulsar wind nebula. Some of the issues that this survey is going to tackle, the sources of galactic cosmic rays. So now I'm going to tell you what cosmic rays are. About 100 years ago, Victor Hess, doing some very dangerous balloon flights, discovered that there were some things very, very energetic in the atmosphere. He called them cosmic rays. They're not rays, they're particles. This is the flux distribution, so this is flux in these funny units versus energy. So GeV, TeV, PeV, they reach the exa-electron volt. That's 1,000 peta-electron volt. That's 10 to the 18 electron volt. The record holder is 320 exa-electron volt. They're the most energetic things we know, okay? Nothing can match this. Forget about LHC. LHC is down here, as you can see. Forget about CTA, forget about neutrinos. They're way beyond anything we can actually imagine. Now, as you can see, there is a little knee here in this distribution, and the experts are convinced that below the knee, the sources are galactic, but we still don't know which sources are producing these cosmic rays. So this is one of the open issues. Also, there's been a lot of effort, but the mechanism by which you can accelerate particles, these are actually protons or nuclei of atoms, at these energies is not really clear. Believe it or not, also the nature of the pulse, so the non-pulsar nebula related radiation is not very clear. Also, there are many binaries in the galaxy, but only some of them are gamma ray emitters. We don't know why. And last but not least, the nature of the so-called pevatrons. These are sources emitting above 0.1 peta electron volt in energy, which have been seen by the LASO, which is the Large High Altitude Air Shower Observatory in Tibet. There was a Nature paper about it a couple of years ago. And LASO detected 12 pevatrons in the galaxy, of course, because, as I told you earlier, a peta electron volt extragalactic photon can never reach us. And only one was identified with a crab. The other 11 are unidentified. Why? Because the spatial resolution of LASO is really bad. So, of course, an obvious improvement is that angular resolution versus energy. LASO is up there, CTA is down here. So CTA will be able to actually nail down the origin of these pevatrons. And on the right, you see the sensitivity. Compare LASO. This is LASO 1 year exposure, and this is CTA 50 hours. So, of course, CTA is going to win by a large amount. Okay, now moving further along to beyond the galaxy. I'm going to discuss an extragalactic survey, which comes from the CTA science paper. The idea is going to be able to have a survey which is going to last about 1,000 hours. It's going to be a blind survey about a quarter of the sky using CTA south and north. Okay, blind survey. We don't have that at the moment, and this is going to be amazing. The main aim is to get an unbiased catalog above 125 GeV down to this funny unit, 6 millicrab. Don't worry, the crab is a flux limit used by energy astrophysics. So it's going to be deep, deeper than we can do right now. And the main point is the following. Of all the blazars because there are mostly blazars detected by HESS, Veritas, and MAGIC right now, 50% were detected where they were in outburst. So our current knowledge of the TeV sky would be like if you guys knew the optical near-infrared skies only through transients, completely biased, okay? So we don't really know what the TeV sky is looking at. And just to give you an example, this is one, a flat spectrum quasar, Resh almost 1, which was detected by MAGIC. Why was it detected? Because Fermi said, guys, this source is in outburst. So everybody, all the HESS, MAGIC, and Veritas facilities rushed to look at it because, of course, since you're not very sensitive, if you are looking at the source which is in outburst, it's more likely you're going to detect it. So, as I said, half of the sources we have now are being detected because they were in outburst, so we have a totally biased view of this TeV sky. So what are the main objectives of the extragalactic survey? Blazars, of course, because they dominate the TeV sky, and we need an unbiased survey. Extreme blazars, these are sources where the gamma ray peak is above 100 GeV, 0.1 electron volt. Again, the theories have hard time modeling these photons because it's very, very hard to observe photons at these energies. Radio galaxies, so if blazars are pointed towards us with the jets, radio galaxies actually have the jets on the sky. And so far, there are 5 radio galaxies detected in the TeV band, and we don't know exactly where the gamma ray photons are coming from. Gamma ray bursts, there are 5 detected so far. One of them is called the boat, the brightest of all time. So those of you who work on GRBs, of course, know about this. GRB 221009A was detected up to 13 tera electron volt. The Nature paper was submitted 2 days ago by the LASO collaboration, and it's the brightest and most energetic GRB of all time. Here I'm plotting energy versus redshift, and there it is. I was at the Gamma Ray conference 2 weeks ago, and theorists have hard problem explaining this energy photons and this energy. So again, this is going to be one of the points that the extragalactic survey is going to address. Blazars. Why should you care about blazars? Well, because they are size of very energy phenomena. They manage to accelerate photons up to 20 tera-electron-volt and particles up to 0.9998 C. That's the Lorentz factor of 50. So we still don't know how, but they do manage to do that. And the reason we know how they do it and why they're so fast, because we study blazars at very high resolution in the radio band. We follow these radio blobs moving with time. We infer the velocity, turns out to be above the speed of light, but that's an illusion. And then with some arguments, you actually get the intrinsic speed, and they're always very, very high. So my favorite definition of blazars is that they're nature's free accelerator, which is why many particle physicists actually have moved to blazars. It's cheaper to study a blazar than to build another LHC. Really, I mean, there is a bunch of physicists now studying blazars because they have a free accelerator there and don't have to build anything under Geneva. So what is CA going to do in terms of blazars, of course? I'm sure that the organizer didn't know about this, but 8 years ago, I wrote a paper about CTA and blazars, and this was quoted by the CTA science paper, so I'm not promoting myself, it was just quoted by them. So with Paolo Padovani 8 years ago, we put everything we know about blazars in the computer, and we simulated the CTA sky at the TeV energies. And so this is plotting, this is a number count, integral number count, number of sources above flux S per square degree as a function of flux. And you see, you have to look at the total numbers which are unabsorbed before the optically near-infrared photons destroy the gamma ray photon, and then they're absorbed here. So this is what you can do right now with the current Cherenkov facilities without having complete samples, and this is what CTA is going to do. So based with what Paolo and Paolo Padovani did with me, we predict that CTA should be seen between 110 and 180 blazars, okay? But again, the strong point is going to be it's going to be a flux-limited sample. So for the first time, we'll be able to build a TeV luminosity function and study the evolution at these energies. And just for your knowledge, so this is the rate distribution of flash spectrum quasars and blazars, BLACs, which are the two main subclasses of blazar. So here you see the rate distribution before the absorption by the EBL. So the peak is actually 1.5. But then once you absorb, because the photons are destroyed, you actually get many sources drop from your surveys, and the peak is below 1. So again, just to show that the effect of this EBL, external background light absorption, is very, very strong. Another main point of CTA is actually this one, which is quite embarrassing. We've been studying blazars for 30 years or more, and we still don't know where the gamma ray photons are coming from. I know it's embarrassing, but that's a fact of life. So there are two contenders. First one is leptonic models. So you have electrons moving fast in a magnetic field. They produce synchrotron radiation, and the same electrons, through inverse Compton emission, boost the low energy photons to the high energy band. And this is called leptonic models because electrons are leptons. The other contender are hadronic models. Here you have protons, high energy protons colliding with protons or with photons, producing pi zeros, which decay and produce gamma ray photons. The same process produces pi plus and pi minuses and produce neutrinos. So the hadronic process produces gamma ray photons and neutrinos. The leptonic models only gamma ray photons. So this is very, very relevant for neutrino astronomy. We, by chance, is one of the topics I've been working on for the past 10 years. And why can't we distinguish between the two? This is a plot by Xavier Rodriguez, who's a postdoc of mine working with ESO right now, where in this paper, he fitted the same data. The data, you can barely see them. Yeah, you see them there, with two completely different models, leptonic and hadronic. The quality of the data is so bad, the uncertainty is so high that we don't distinguish them. With CTA, of course, it's going to be very different. So this is now real data in black for a blazar. And you can see, you can fit the same data with an hadronic scenario and electronic scenario, because the uncertainties and energies are very high. CTA, these are simulations, of course, will be able to nail down is it electronic or electronic, because the quality of data is going to be so good. Yeah, one slide. That you'll be able to distinguish between the two. And this has amazing implications. I have no time to get into that, but to do with neutrino astronomy. So the first neutrino source seen by IceTube, which is a neutrino detector, was a blazar, and we still don't know why it was detected. And so by having CTA looking for hadronic emission, protons means they produce gamma rays and neutrinos. It's going to be a boost for neutrino astronomy. I'm done. So what you need to remember. CTA is going to be a game changer because of its size, sensitivity, and angular resolution. Gamma radiation is the most energetic radiation of the spectrum, and it's produced only in some extreme conditions of the universe, so sampling extreme physics. I repeat again, at the moment we don't have any flux-limited complete surveys of the TeV sky, so whatever CTA is going to do in this respect is going to be a game changer, a breakthrough. And last but not least, CTA is going to be very important for blazar studies and also for multi-messenger astronomy, neutrinos, and cosmic rays. Thank you very much.